Inner products, this whole chapter deals with inner products. Um, an inner product, it's the definition of it is actually in two pieces. It says that an inner product, which is on some real vector space, V, which we took a lot of time in the past couple of weeks trying to define a vector space, and you remember that a vector space must satisfy 10 axioms. Those axioms must be applicable to vector addition and scalar multiplication. So an inner product defined on some real vector space is a function that associates a real number. You may think about that as just being the plain old dot product, if you will. Associates this number, the inner product of U and V, with vectors, U and V, that's in the vector space, the V, in such a way that the following axioms are all satisfied for all vectors in the vector space and for all scalars, K. 4 axioms must be true. And forgive me, last time I taught this, I did put some information in this lecture that somewhat tried to speak to the generality of the inner product. This is the introduction of it. In terms of the math that we study, that's very bigger than this in terms of what we look at in upper level mathematics and in graduate school. What is this trying to say, or what are we trying to get at? And I made some comments last time, and try to go back and find those notes, and if I can, I will put those in the into the PDF for you. But I will make a statement in terms of what we're trying to do with this, so that you have a somewhat of a, not just an abstraction, because a lot of this would be abstractions, but a more concrete image of what's actually going on here with the inner product. It does do two things. The first thing that it does is it says that if you give me a set of vectors, that in such a way with those vectors I can multiply them together with a very special type of multiplication, and that way that we multiply here in this sense with these vectors would be called the inner product, or for layman's terms, the dot product. So one, how do I associate vectors in terms of multiplication? It's going to be an inner product. So that's the first thing. And then the second thing that's going to be associated with the inner product is how to take, multiplication no more than just summation, how to take that summation to be able to compute the length of a vector, whether it's the length of a vector or it's the distance between one vector and another. So it's really the two main things that we want to try to see with the inner product. One, how do you multiply vectors? And then secondly, how do you measure the length of a vector? The inner product is something that you've already seen before. We just didn't say it was an inner product, but you've been dealing with it probably since maybe middle school, high school. Do you recall taking or using the so-called distance formula? The distance formula between 2 points, P and Q, and you take the square root, that's the inner product. Right? And so that distance formula is no more than the length or the norm. In calculus 3, talk about the norm, talk about the cross product, talk about finding the area of a parallelogram by being the norm of the cross product of the two adjacent vectors. That's an inner product. So how do you measure the length of from one point to another? Here is the standard, we call it Euclidean inner product, because we're dealing with vectors or that deals with lines that are said to be straight. Now what does that mean in terms of an introduction to this chapter and to this idea of an inner product, what are they saying? The so-called standard inner product is not the norm. And that's a play on words because we take the norm, and the norm is defined as being the length or the magnitude. It's pretty good because it is not the norm in that there are other inner products out there that exist. There are other measurements of measuring between one point and another point. It just depends on what are you looking at in terms of how fast can you get from one particle or one point to another point. You can talk about that distance based on the speed or the velocity going from this point to another point. Or you can talk about the distance from one point to another point, trying to avoid distractions between points A and B. And so the distance may not be a straight line. The distance could be curvature. The distance could be sawtooth wave, where kind of you go here, then you turn, and then you cut, and so you may have to avoid certain buildings, certain places in a city to be able to get the most practical or most economical or the most scenic route. And so when you have your smartphone navigation system, and it asks you, in terms of how do you want to get to a certain location. Do you want to take the scenic route? You want to go through the city? You want to avoid the traffic? They're actually using engineering tools based on inner products. And so each mode that you pick, whether it's the scenic route or the city traveling or to avoid traffic or what have you, they're talking about different measurements of lengths going from one point to another in a product. The information that I want to share with you, that I try to put here in the PDF, in terms of the abstractions in mathematics, deals with one of the sub-tiers of this course. I don't know if it's a sub-tier or if it's even considered a hierarchy, and this class is considered probably a sub-tier of it, would be analysis or real analysis. One component of that is called topology, and that is the study of measurement. It is the study of measurement. Its foundation would be this so-called inner product right here. The introduction of that course starts here with this information. Each tier of these axioms would give you certain types of spaces. Now, I just make mention of three, and then we'll move on. Some of the three widely used spaces today in inner products in mathematical science would be one called a metric space. The second one is called a Hilbert space. And then the third one would be a Barnard space. And they all make use of these topics here. If I have time, I try to categorize that and put that in the PDF for you. So here, the four axioms that define the basis for inner product. One is the inner product itself says that this is how I associate, if there's a such thing as multiplying matrices, we'll call it this dot product or this inner product. Now that inner product can be explained or manipulated or simplified in four ways. One, we say that the inner product is symmetric. So if you say that the inner product of vectors u and v, that result is the same thing as the inner product of v and u. Now, one thing I want you to understand is that the inner product, it doesn't matter what size the vector space, the basis or the dimension of that vector space would be. Once you apply the inner product of two vectors, then that codomain, that range, is the real number system. So you get here, you take the inner product of vectors, the result is a scalar, right? The result is just one term. So the mapping So here, inner products maps here Rn into the real space. That is, the result of the inner product is a scalar. So here we have symmetry, we have additivity. Now, to you and me, you would think of that as just being the distributive property, and that's all it is. So the axiom of additivity is simply the distributive property. Number two. Thirdly, homogeneity. Have you seen that before? If, say for example, maybe in the class differential equations, there's a component where we talk about homogeneous differential equations. We say that a differential equation, if it's homogeneous, then you can solve by using some kind of fancy substitution. Right? So that property comes from here, homogeneity. Right? Which basically simply says that if there's a scalar multiplied to a vector, that scalar is the same thing as it multiplied to the entire inner product. Positivity axiom. Basically, it says that here the inner product of a vector with itself is either positive or zero, right? And that this inner product of a vector with itself is equal to zero if the vector is a zero vector. A real vector space with an inner product here that satisfies these four axioms is called a real inner product space. Now, definitions of the norm, or that is, how do you measure the length and then the distance between two vectors. This is very standard. So here the norm of a vector v is what you've seen before. It's the square root of each component of the vector summed up squared, right? So the norm of v, what is that? That's just no more than the square root of the inner product of v with itself. Here, the distance between two vectors, u and v, in some vector space is the typical, the distance d of u comma v, and that's going to be the square root of the differences of each component, the corresponding components, the difference of those. So u sub 1 minus v sub 1 squared plus the summation of the like. So again, you've seen that distance formula before, and you've also seen the norm, the magnitude before. It's the same one that's used in physics as well. So if you want to get a unit vector, take any vector, find its norm, and divide the vector by its norm. That gives you a unit vector. The unit vector is said to be any vector with length or magnitude 1. As properties of norms and distances. I think in the next class when we come back, we'll prove some of these properties, which is most important to our study of the mathematics. Let u and v be vectors in a real inner product space v, and let k be some scalar. So here, what they're going to do is basically apply the previous four axioms, that is the axiom of symmetry, additivity, positivity, and homogeneity. Apply those axioms from the definition for the inner product here to either the norm or the distance. Same concept. basically. So that is that here the norm says that the length of a vector is either positive or zero. The key is that the magnitude or the length of any object is not negative. That's the only thing they're saying there. The only vector that measures zero is the zero vector itself. Here for the so-called positivity, that the norm of a scalar times a vector, here's the same thing as the absolute value of the scalar times the norm of the vector v. So you want to be very careful about the positivity of the scalar, because remember, this norm is a square root, right? That norm is a square root, so you got to be careful with negative signs and that kind of thing. Here the distance is symmetric, so the distance between u and v is the same thing as the distance from v to u. Right? Here the distance between two vectors is going to be either positive or zero. Here we definitely get zero if the two vectors are the same, right? If and only if u is equal to v. Now here's some examples of inner products, and I believe that when I stated these examples, hopefully somewhere down there I also said I'm giving you some of the standard inner products. There are some standard inner products, but then there are some inner products that have been generated or populated by either mathematicians or scientists. So here, this is a matrix inner product. Let A be an invertible square n by n matrix. Then the inner product of u and v associated with the matrix A is said to be this. So it's the transpose of the matrix A times v, and then times here the matrix A times u. Now what that does, because two ways you can compute this. You can compute this by taking the inner product of A times u with A times v. Now if you do that, it's going to be the same thing as the transpose of AV times AU. That'd be neat to look at, and I think we got an example down here where we'll try to make some use of this particular inner product. Secondly, let U and V be two n by n matrices. Then this formula, the inner product of U and V, is said to be the trace. Remember that? The trace, TR, the trace of U transpose times V. So basically you're going to take the transpose of the matrix U, multiply it times the matrix V, and then take the trace of that, and that gives you here this particular inner product of those two vectors. Number three is going to be a standard inner product of polynomials. So here the inner product of polynomials, P sub n, if given two polynomials P and Q here of n dimension or n plus one dimension, then the standard inner product is given by here the sum of the corresponding components multiplied, right? Again, standard. The norm here that is given for polynomials is also going to be standard. So the norm of P here, again, standard. Now, numbers 4 and 5, in terms of functions, an inner product here of the space of all continuous functions on a closed interval from A to B, a very big space. This, by the way, is a vector space. So here we call this inner product on this space of functions, the inner product is an integral. So let f and g be two functions on this space of continuous functions from A to B. The inner product of the two functions, f and g, is said to be the integral from A to B of f times g. Its associated norm is here also given. So here, let f be a function on this very big space of continuous functions on the closed interval from a to b. Then the so-called norm of the function f. Always the same notation in terms of the square root of the inner product here, but this is applied now to continuous functions. So this is the square root of the integral from a to b of the function times itself, dx. Let's look at some problems, and we'll finish this day with these problems here, and I think we should be okay. Now, let R2, the space of all two-tuple vectors, have a weighted Euclidean inner product. So basically, they just put weights to the so-called standard inner product. The weights is 2 times u sub 1 times v sub 1, and then plus 3 times u sub 2 times v sub 2. That's not standard because the standard inner product would be absent the 2 and absent the 3, right? That would be the standard inner product. So based on what they give us, then we want to compute here the inner product of u and v, given these values for vectors u, v, w, and the scalar k. So here we compute this. This is going to be this 2 times u sub 1 times v sub 1, where u sub 1 is 1 and v sub 1 is 3, plus 3 times u sub 2 times v sub 2, where u sub 2 is 1 and v sub 2 is 2. So here we get 6 plus 6, we get 12. Again, A, B, C, and D, and E would make use of this weighted norm, or this weighted inner product, excuse me. So here, this, you recall, is the same thing as K times the inner product. That's V and W, not U and W. So K, I believe, is 3. And then this is going to be the inner product of V and W. Let's see here. Let's go ahead and put the values of V here. That's 3, 2, and then W is 0 and -1. So this is 3 on the outside, and then that inner product is 2 times the product of the first components, 3 times 0, plus then it's 3 times the product of the second components, 2 times -1. So that's 0. So here we get -6 and 3, -18. Here, this is the so-called distributive property. So this is the inner product of U with W plus the inner product of V with W. So here, first, the inner product of U with W, and U again is 1, 1, and W is 0, -1, plus the inner product of V, 3, 2, and W, and we found that one up here without the K. But this, so here, this is going to be 2 times the first component, 1 times 0, and then plus 3 times the second components. And then here, this is again 2 times the first component, plus 3 times the second components. So this is 0 here. This is -3. That's 0. And this is -6. So we get -9. Now what about the norm? The norm of V. So this is the square root of the inner product of V with itself. So here, this is the square root of, here the vector V is 3 2 here, and this is 3 comma 2. So this is the square root of, here I use that same given weighted inner product, so it's going to be 2 times the product of the first components. So this is 2 times 3 times 3 plus 3 times 2 times 2. So this is here 18 plus, we get the square root of 30. What about the distance? Here the distance is defined as the norm of u minus v. Right? This is the same thing as the square root of, here the norm of u minus v with itself. Well, this is the square root. So here we just find u minus v. So it's this inner product of u minus v. Let's see here, that's the u minus v is 1 minus 3, so that's -2, comma 1 minus 2, that's -1. So this is -2, comma -1. Inner product with itself again, -2, comma -1. So this is the square root of, here I use the formula that they give me, 2 times the first component plus 3 times the next one. So this is 2 times -2 times -2 plus 3 times the second components. So here we get 8 plus 3, the square root of 11. Now, number 2, now again, if in the problem, if it's not a weighted inner product, then typically you would just simply use the standard inner product, which is a whole lot easier. Number 2, use the inner product on R2 generated by the matrix A to find the inner product of u and v for the vectors u and v. Here, if I'm given 2 vectors in a matrix and you want to find the inner product associated or generated by the matrix, you have to use this guy right here. So here the inner product of u and v would be AU dot product with AV, or the transpose, right? So here this inner product is AU dot with AV, or AV transpose here times AU. Okay. So we have to find A times V, and then we have to find A times U. So first, A times V here the vector V is 6, 2. So this is a 2 by 2, this is a 2 by 1. So the result would look like the vector V standing up. It'll be another 2 by 1. So we get 24 plus 2 is 26. Then we get 12 minus 6, we get 6. And then we need to find AU, 4, 2, 1, negative 3. Times U, this is 0, negative 3. So we get 0, negative 3, we get 0, and 9. So here the inner product of U with V is, you can take this and just take the dot product of negative 3 comma 9 with 26 comma 6. You get the same thing here as the transpose of AV times AU. Well, what is that? Well, AV, if you transpose that, that becomes here a row, 26 and 6, times here the column of AU, which is negative 3 and 9. So this is 26 times negative 3 plus 6 times 9. So what did you get there? Get negative 24. Good. Okay. Now, when it says the standard, compute the standard inner product, that's what we like because it's just very straightforward. So compute here the standard inner product on the space of matrices of size 2 by 2 of the given matrices. So here the standard inner product of matrices U and V would be here just the multiplication of the corresponding entries, then you sum that up. So it's going to be 3 times negative 1 plus negative 2 times 3 plus 4 times 1 plus 8 times 1. So we get negative 3 minus 6 plus 12. So here we just get 3. So the standard inner product is always not difficult. Here again, the standard inner product for polynomials. Think about P as having the components negative 5, 2, and 1, and Q with components. And then the components must be in the same order. So if it's going to be in ascending order, then all polynomials must be in ascending order. If they're going to be in descending order, that's fine. But they all must be in descending order. So you can say 1, 2, negative 5, and then over here you'll say negative 4, 2, and 3. Doesn't matter, but as long as you're consistent, then that's fine. So the inner product, P and Q, negative 5 times 3 plus 2 times 2 plus 1 times the negative 4. So negative 15 plus 4 minus 4, just get negative 15. the norm and the distance, still same two polynomials. So here the norm of P. We got the components for P again. -5, 2, and 1. So here, this norm is the square root of the -5 squared plus 2 squared plus 1 squared. So this is the square root of 25 plus 4 plus 1. So here we get the square root of 30. The distance between P and Q, this is the same thing as the norm of P minus Q. So the norm of P minus Q, again, Q has components 3, 2, -4. So we do the subtraction between P and Q. That gives us -5 minus 3 is -8. 2 minus 2 is 0. 1 minus a -4 is 1 plus 4 is 5. So then we just take its norm. So we get -8 to be squared, 0 to be squared, 5 to be squared. So we get 64 plus 25. So we get here the square root of 89. Okay. That's the one. Any questions so far? Here, what if you have matrices? Find the so-called norm and the distance. Here, using the standard inner product. Again, I don't know about you, but I like the word standard. So here, the norm for U is going to be the square root. Each component squared, you add them up. So this is 3 squared plus -2 squared plus 4 squared plus 8 squared. So we get here the square root of 9 plus 4 plus 16 plus 64. I think that can be broken down. Yeah. That's it. And then the distance between U and V. This is the norm of U minus V. This is the norm of, take each corresponding component, do the subtraction. So 3 minus a -1 is 3 plus 1 is 4. -2 minus 3, -5. 4 minus 1 is 3. And then 8 minus 1, 7. So we get the square root of 4 squared plus -5 squared plus 3 squared plus 7 squared. We get the square root of 16 plus 25 plus 9 plus 49. Now, let's look at the last problem. How do you compute inner products, norms, distances based on functions that are on the space of all continuous functions on some closed interval? And it's a closed interval because that gives way to a definite integral. If it's the space of all continuous function on the open interval, then by all means, that's how we define an indefinite interval. And what I'm trying to do with each problem that I'm working is I'm really giving you just a model type of every problem that's going to be on this test. Right? So I've cut down and cut out all the fluff, the fluff. Thank you. Get my U's and whatever. All the fluff. Yes, I've cut out all that stuff, and I'm just going right to the problems that I'm going to be testing y'all on. So you get this information right here, you'll be fine. So with this particular problem, here we compute the first, the inner product of P and Q. So here, P is 1 and Q is x squared. So the inner product based on this definition, you're integrating from -1 to 1. Here, P times Q, x squared dx. That's just the integral from -1 to 1 of x squared dx. So that gives us 1/3 times x to the third. That's evaluated from -1 to 1. -1 to 1. So we get 1/3 plus 1/3. We get 2/3. The distance is said to be the norm of P minus Q. This so-called norm is going to be the square root of the inner product of P minus Q with P minus Q. So this is the square root of the inner product of P minus Q, comma, P minus Q. So this is this, I'm going to put this whole integral from -1 to 1. P minus Q is 1 minus x squared. But then it's times P minus Q again, so it's times 1 minus x squared. Dx is all raised to the 1/2 power. Now, in terms of functions and how you compute the so-called lengths here between these two functions, we call this realm of mathematics. This is the so-called inner product for a Hilbert space. And again, I'm trying my best to classify it in the PDF and try to send that to you hopefully tomorrow if I can get to it. You talk about, I was very hurt when I got the news of Matthew on yesterday. Let me tell you, I was really hurt because last week I got a phone call from another mother at our church that her son had went down to Lowndes County because their family is from down there, and this young brother was driving down there, and apparently he was taking his medicine, and he got very sleepy and drove off the road, and he was instantly killed. And this was last week Tuesday. He had just turned 48 that was his birthday on that day. And this young brother would come to the church every Sunday, and he'd come sit in the same spot. He was very quiet, very shy young man, so he didn't really talk much to people. And I don't know if a lot of people really even knew him, because I made mention at church. I said, young brother, called his name. I said, he'd come here for the past few years. He would sit in the same seat, and that he's passed away. And people came up to me and said, "Who are you talking about?" I said, "He's been coming here for the last, I don't know, 5-6 years." But anyway, that got me down last week, and then heard from the mother, from my dear young friend here, and same situation. So very sad, but the Lord knows all. So here, this is the integral from -1 to 1. This is just 1 minus x squared to be squared. Same thing from before, dx raised to the 1/2 power. So just regular integration. We're going to FOIL that out. Minus so this is x minus 2/3 x to the third plus 1/5 times x to the fifth. It's evaluated from -1 to 1. So evaluate this at 1 minus 2/3 plus 1/5. Then at -1, so this is minus -1, is plus 1. They're all odd, and so they maintain their nature in terms of signs. So this is the square root of 2 minus 4 thirds plus 2/5. So this is going to be 16 over 15, or you can just say 4 over the square root of 15. Part C, this so-called norm of P is the square root of inner product of P with itself. Well, P was it's the function 1, I believe. So this is the integral from -1 to 1 of 1 squared dx. Right. So here we integrate 1, we get x evaluated from -1 to 1. Don't know why I like to keep writing -1 to -1. So this is 1 plus 1. We get just the square root of 2. Is that it? Okay. This last one. This norm of Q is the square root of Q with itself. So this is the integral from -1 to 1. Q is x squared
times x squared dx.
1/2 power of that.
So this is the integral from -1 to 1 of x to the 4th, dx. One-fifth x to the 5th, evaluated from -1 to 1. So here we get 1/5 plus 1/5. It's going to be the square root of 2/5.
Any questions there? Look at part B.
See how this is broken down, this norm of p minus q? Well, this is the same thing as we said here, the inner product of p minus q and p minus q.
Now, if we use the axiom in terms of that distributive or that additive axiom,
we get, this is the square root of the inner product of p and p minus 2 times the inner product of p and q plus here the inner product of q with itself.
Right? Now, I think we have all three components there. We have the inner product of P and Q, and then it's going to be times the -2. That'll give us the middle component, right? Right?
Michael?
Yes.
Is that right?
Boy, I tell you all some slackers, man. Woo. Okay, here's what I want you to do. We got 7 minutes. I need you to compute this inner product of P minus Q using, this is the square root, using the inner product of P and P, then minus 2 times the inner product of P and Q, plus the inner product of Q with Q. And you should find all the information here already that we've worked out. Just configure that into this square root. So you're going to be working it different than how I worked it out right here. It's the same thing as part B, but you're looking at this inner product in a different light. So I want you to work it out just like this right here. Just show me those three parts, right? And you should come up with the same thing that we came up with down here, and that was 4 over the square root of 15. And something that we can give you on the side.
Notice here that this inner product of P with itself is the same thing as the norm of P squared.
Because the norm is the square root, right? So if I square that square root, I get the basic inner product. So this norm of P, did I find that? Did I find that somewhere? I found it right there, right? And then you also, look, this inner product of Q with itself is going to be the norm of Q squared, right? We found that downstairs as well. Right? Put those three numbers together and compute that in that square root. Let's see if you still get 4 over the square root of 15. You should.
So what do you need there? The norm of P, you calculated that. That was the square root of 2. And then you got the inner product of P and Q. That was the first thing you did, 2 over the square root of 3. And then you got the norm of Q. I think that was the last thing we did. That was the square root of 2 over 5. If you put these three quantities here in this square root, let's see what you get.